floating weightlessly in orbit looks completely serene on film, but long-term, the absence of gravity strips the human body down like rust on metal. This image captures the reality of that decay. Astronauts running medical experiments on a crewmate inside a tight orbital module. In microgravity, bones immediately begin to lose density, leaving the skeletal system dangerously fragile, and the cardiovascular system takes a hit as well. This astronaut is strapped into a specialized resistance machine because without gravity to fight against, muscles shrink and the heart weakens from the sudden lack of physical workload. If our physiology physically breaks down after a few months in orbit, we are barred from deep space. We remain stuck in low Earth orbit as fragile tourists. To truly live among the stars, we literally have to build Earth's physical forces and drag them into the void with us. Engineers return to one mechanical solution: spinning a hub-and-spoke station to create centrifugal force, simulating the downward pull of home. To safely manage long missions, the station needs half of Earth's gravity, requiring a 130-foot radius rotating at 5 RPM. We actually started testing this decades ago. During Project Gemini 11 in 1966, a crew strapped their spacecraft to an Agena target vehicle using a 100-foot tether, which you can see stretching across the frame here. By firing their thrusters and spinning the two connected vehicles like a slow-motion lasso, they generated a microscopic fraction of an outward pull. It was tiny, but it proved astronauts could successfully manufacture their own gravity in orbit. In 2011, NASA mapped out the Nautilus X concept, which planned to integrate an onboard spinning centrifuge. The goal was to keep crews physically intact during the long, multi-month transits to the Moon or Mars. But spinning a massive structure in the vacuum of space introduces a terrifying logistical hurdle: docking. Maneuvering a spacecraft to meet a stationary object already requires immense precision. Approaching a giant rotating structure means an incoming ship must perfectly match that exact speed and angle while drifting at thousands of miles per hour. If the pilot miscalculates their timing by even a fraction of a second, the ship will violently bounce off the station's hull, instantly tearing the entire structure into a high-speed debris cloud. Generating artificial gravity forces engineers into a high-stakes mechanical gamble. A single math error destroys the crew's oxygen supply, their safety, and their only vessel back home. While we try to build survivable habitats in orbit, we also have to look outward at what happens when a naturally habitable environment turns hostile. Take a look at these two views of Venus, a planet nearly identical to Earth in size and gravity. Despite those similarities, its surface is a toxic pressure cooker hidden beneath dense acid clouds, with atmospheric heat intense enough to melt metal on contact. To figure out how our planetary twin broke bad, NASA is planning the Veritas mission for 2031. It will use spectroscopy, a technique that measures how different materials interact with light, to pierce the cloud cover and map the hidden scars on the Venusian surface. Around the same time, a probe called DAVINCI will drop straight through that crushing atmosphere, measuring chemical signatures top to bottom, searching for evidence that Venus might have once held actual liquid water oceans before boiling them away. We spend billions of dollars sending hardware to a dead, toxic world because it serves as an essential reconnaissance mission. We need to measure the exact chemical mechanisms that can permanently destroy a planet's ability to support life. Up in Earth orbit, we face a third survival front entirely of our own making. Decades of launches have polluted our spaceways with dead, metallic satellites that create hazardous shrapnel. To clean up the orbital environment, Japanese researchers recently launched LignoSat, a tiny, radical experiment built almost entirely out of magnolia wood. Instead of relying on metal fasteners that can warp or break, the design uses traditional Japanese wood joinery. These precise, glue-free and screw-free connections hold the structure together against extreme radiation and temperature swings, while ensuring the wood burns up completely cleanly during re-entry. Surviving the punishing physics of the cosmos means we have to abandon standard aerospace assumptions and test deeply sustainable, Earth-grown materials in a total vacuum. Spinning gravity hubs, robotic atmospheric probes, and wooden orbital satellites seem completely unrelated, but together they form a unified blueprint for deep space survival. To conquer an environment that aggressively tries to freeze, irradiate, or crush the human body, We have to rely on counterintuitive engineering hacks. Tying spacecraft together with tethers or building orbital centrifuges always sounds like impossible science fiction, right up until the second the hardware successfully activates in orbit. Our future depends on actively challenging the physics of the void. We have to take a universe designed to destroy us and manually engineer it into a permanent home.